Chapter 5.1. So, as a word of warning, Chapter 5 is probably the most difficult first semester topic. So, if you have an A game and you haven't been there already, you'd want to make sure that you're trying to stay as focused as possible here for Chapter 5. And we'll talk as we go about why I'm saying that and what you guys can be doing. When we talk about an identity, what we really are saying is that an identity is just like an equality statement that's true for all values of the variable. So something kind of trivial as this, you could call an identity, right? That's true for all values of x. In this course, since we're talking about trigonometry, the identities that we're going to talk about here are going to be involving our trig functions, sine, cosine, tangent, etc. So I'm going to collect these identities here in this section into a few different categories, some of which we've expressly kind of talked about, and we're just going to regroup kind of all together in one place and talk about them again. Some of them we've kind of hinted at. We'll kind of go back and show you oh, we've already talked about this concept, and if we apply it here, we get these identities. And some of them will derive from whole cloth. Okay? So I'll try to be clear about how I'm getting the information that I'm writing down. The first set of identities that we're going to talk about are called the reciprocal identities. And these six are things that we've talked about expressly. So way back when we talked about right triangle trig and we defined the 6 trig functions, we talked about the observation that sine and cosecant were reciprocals, that cosine and secant were reciprocals, and that tangent and cotangent were reciprocals. So this is just me recollecting that information kind of all into one place. I'm not going to spend really any more time describing why these relationships are true. We did that way back when we talked about right triangle trig, and it basically stems purely from the definitions of how we define these functions. The next 2 identities are called the quotient identities. And these 2 are also things that we've talked about expressly. So the first one, that tangent theta is equal to sine theta over cosine theta. We just talked about this when we put together or described how to find tangent on the unit circle, right? Tangent is y over x, or y was the value for sine and x was the value for cosine. And if tangent and cotangent are reciprocals, then cotangent would be cosine over sine. The next set of identities we're going to derive ourselves. I'm not going to name them until the very end because The name kind of gives away something here that we're going to use to do the derivation that I don't want to give away right away. But we'll collect them together and put them in the same kind of category, just like we did the identities preceding this. But we're going to kind of build up to how we get these things. Okay with that plan? Okay. So suppose we have a right triangle. And I'm going to label this angle as my theta. Relative to that theta, this side is the adjacent, this side is the opposite, and this side is the hypotenuse, right? What I'm going to do is I'm going to look at sine squared theta plus cosine squared theta. Using my right triangle definition, I know that sine is opposite over hypotenuse, right? So sine squared is going to be opposite over hypotenuse squared. Similarly, I know that cosine is adjacent over hypotenuse. So cosine squared is going to be adjacent over hypotenuse squared. Everybody so far so good? Okay. And I know that if I square a fraction, how do I do that? Square the numerator and square the denominator, right? So that's going to give me opposite squared over hypotenuse squared plus adjacent squared over hypotenuse squared. Here, I notice that I have a common denominator, right? Both of these fractions have the denominator of hypotenuse squared, so I can just write these as a single fraction. And now I'm going to ask, what does opposite squared plus adjacent squared have to equal? Let's go back and look at our right triangle here. Opposite squared plus adjacent squared has to equal hypotenuse squared, right? Why? It's the Pythagorean theorem, right? And obviously, hypotenuse squared over hypotenuse squared is 1. So I have then the relationship that sine squared theta plus cosine squared theta is 1. That's going to be the first of my yet-to-be-named 3 identities. I'm now going to create 2 different versions of this identity by, in the first case, dividing both sides by sine. But instead of saying dividing both sides by sine squared, I'm going to write that I'm multiplying by 1 over sine squared. It's really the same thing, but it makes the notation a little bit easier if I write it as a multiplication rather than division. So that's going to give me sine squared theta over sine squared theta, cosine squared theta over sine squared theta equals 1 over sine squared theta. Well, sine squared theta over sine squared theta is obviously what? 1. I recognize cosine theta over sine theta is cotangent. So cosine squared over sine squared is going to be cotangent squared. Similarly, I know that 1 over sine theta is cosecant. So 1 over sine squared theta is cosecant squared theta. That'll be the second version. And to get my third version, what do you suppose I'm going to do this time? Yeah, I'm going to divide by cosine squared. So here I notice that I have sine squared theta over cosine squared theta. I know that sine over cosine is tangent. So this is tangent squared theta. Cosine squared over cosine squared is going to be 1. And then I know 1 over cosine is secant. So 1 over cosine squared has to be secant squared. So if I take all three of those together, we're going to call those the Pythagorean identities. Now, these three identities are a little bit different than the other ones that we've looked at so far because these involve addition and subtraction. The other ones involve really only like division, basically. So I can do a little bit of rearranging on these by adding or subtracting things from both sides. So for example, I could rearrange this by subtracting cosine squared from both sides to write this identity in terms of sine squareds. Or similar, I could subtract sine squared from both sides to write it in terms of cosine squareds. So those are also options. We're not going to write out all those possibilities for each one of these, but keep that in mind that those are still valid identities that that may be useful. In particular, those two that I wrote down there are often things that will get used, which are, again, just versions of this same Pythagorean identity. As an aside, why do you think we called this a Pythagorean identity? Do we have to use to derive this? The Pythagorean theorem, right? So. All right. The next ones are called the cofunction identities. So you guys have recognized that so far that we have like sine and cosine. We have secant and cosecant. We have tangent and cotangent. Has anybody figured out what the co stands for? All right. Well, let's point out something on the unit circle. let's say we look at sine of 30 degrees. That's going to be 1/2, right? Where else is cosine equal to 1/2? At 60 degrees. What's the relationship between 30 and 60? They're complementary. So the co in cosine, cosecant, and cotangent stands for complementary. These are considered complementary functions. In that sine of theta is equal to cosine of the complement of theta. Like what we saw up there, that sine of 30 is equal to the cosine of 60, which is the complement of 30. So that's going to be our next set of identities. The way we're going to write those is we're going to write them in radians. So instead of writing 90, we're going to write pi over 2. But pi over 2 minus theta is really just the complement of theta, right? Everybody can see that? That's the way I'm reading that in my head. And we could write them in both directions. So you guys remember from way back at the beginning of the semester we talked about odd and even functions? We said for even functions that f of negative x is equal to f of x. And we described these even functions as being symmetric about the y-axis. And then for these odd functions, we describe them as f of negative x is equal to negative f of x. What was this? Was it 180 degree point symmetry about the origin? Well, let's think back about the graphs of sine, cosine, and tangent. So what kind of function is cosine? Is it odd or even? Looking at the graph there. Is it symmetric about the y-axis, or does it have that 180-degree point symmetry about the origin? Symmetric about the y-axis, right? Looks like it's a mirror reflection of it across the y-axis. How about sine? That's odd. And tangent? Tangent's odd also. So again, for odd, you're basically looking at to see if like quadrants 1 and 3 are reflections, or quadrants 2 and 4 are reflections. They have to be kind of like diagonally symmetric. So if I take that information then, I can generate what are called the odd-even identities, which are basically just using these two properties of odd and even. So since sine is odd, sine of negative x would be negative. I don't know why I'm using x's here. Let's just use theta still. Been using those throughout. Similarly, since tangent is odd, I can say tangent of theta is equal to, or tangent of negative theta is equal to tangent of theta, or negative tangent of theta. Since cosine is even, I can say cosine of negative theta is equal to just cosine theta. And the nice part is, because sine and tangent are odd, their reciprocals are also going to be odd. Because cosine was even, its reciprocal is also going to be even. So I can say the same thing about the reciprocals of each of those. Okay. Oh, nope. And this secant isn't either. It's because those are even functions. So I'll put a plus sign there just to make sure that everybody's clear on that there's not a negative in front of those ones. All right, that's the last of the identities for this chapter. We have a second chapter later on that contains some more identities, but this is as many as we have for this first chapter. So let's do some examples now. And we'll start with a problem that looks at first glance very familiar. So this first example says, find sine theta if tangent theta is equal to 3 and cosine is negative. So, at first glance, you say, oh, I can do this problem like we did in the previous chapter, in chapter 4. I could use like an inverse function to find the value of theta, and then use the fact that cosine is negative to figure out which spot in the unit circle I'm looking at, or where my answer needs to be, and then I can use that answer and plug it in to find the sine of theta. The drawback to that is you don't get an exact answer. You're going to need to use your calculator to do that, because tangent of 3, or tan theta is equal to 3, is not a unit circle value for tangent. However, if I do want an exact answer out of this, I can get one, but I have to use some of these identities to do that. So the first thing that I'm going to do is I'm going to use the fact that tangent is equal to 3 to figure out a value for cosine. So I have an identity that relates tangents and 1 over cosines, or secants, together. If tangent is equal to 3, tangent squared would be 3 squared. To solve for secant, what would I need to do? Square root both sides. And when I square root both sides, what happens? What do I get? How about a plus or minus? Everybody's okay there? And I know secant is 1 over cosine. And if I do the reciprocal then of both sides, I have that cosine is plus or minus the square root of 10. Or 1 over the square root of 10, excuse me. But remember, cosine is negative. So really, I don't have plus or minus. I have just the minus. I'm going to put that on ice for just a moment. We'll come back to you. Now I'm going to go back to the fact that I know that tan of theta is 3. I still need to figure out a way to get sine involved here. Well, I can do that because I know that tangent is equal to sine over cosine. That's just using the quotient identity. And if I multiply both sides by cosine theta, I have that sine is equal to 3 times cosine theta. And then I can just substitute in my value for cosine theta, right? Which would give me 3, or negative 3 over the square root of 10. Is that the way I want to write my final answer, though? No. What would I want to do here? I'd want to get rid of the square root in my denominator. The way I would get rid of that would be rationalizing the denominator. That means I'm going to multiply the top and bottom by the square root of 10. So my best answer here would be negative 3 root 10 over 10. So notice how fundamentally different this problem was in approaching it this way than what we did in the previous chapter. Did I use an inverse trig function at any point during this process? No. Did I have to go draw locations on the unit circle for where angles are? No. Kind of nice, right? Kind of nice. Okay. Let's do another example. This will be slightly different. And the examples from here on forward in this section will all kind of be of this type, where we're asking you to simplify the expression So when I talk about, or when the direction says simplify, what do we mean by simplify? Is the expression that I'm left with, it should have fewer terms and or fewer factors and or like no fractions. So these are all things that like a simplified answer would look like. right now, this answer has two terms, right? It has sine cubed, and there's the first term, and the second term is the sine x times cosine squared. If I look at the first term, that has one factor. It has sine 3 times, but still just the sine. The second term has sine and cosine, so it has 2 factors in the second one. Do you guys see that? Really, the best case scenario for any simplifying problem is to get it down into a single trig function. That would be our best case scenario. So to do a simplifying problem, we're going to be using combinations of our identities that we just had talked about, as well as like basic algebra techniques. So that could be like, how do we add fractions? Could be some factoring or some foiling or any of these kind of basic algebra kind of skills to rearrange things. Everybody okay with that so far? Okay. So, let's take a look at this. Is there anything that we can do here? What would you want to do first here? So this is usually the hardest part for students, is coming up with what to do. In general, what I would suggest is I would start by looking for any kind of basic algebra thing to do first before I look at trig identities, although that's not a hard and fast rule. Do we see any basic algebra thing that I could do here? Well, I don't have like terms, so I can't add right the way this is. Is there any factoring I could do? Good, I could factor out a sine x, right? There's a greatest common factor of sine between the two terms. So I can do that, right? Okay. Do you see anything to do now? Yeah, now we see an identity obviously staring at us in the face, right? We know that sine squared plus cosine squared is 1. And 1 times sine x is just sine x. And as we mentioned, the best case scenario is to get down to a single trig function like that. So here we are done. So let's say we have secant x minus 1 times secant x plus 1 all over sine squared x. What do you guys think we should do first here? Okay, when you say combine the secant, how are you going to do that? Foil out the 2 parentheses. Yeah, I like that idea. Again, I noticed that if I FOIL these out, do you notice anything about these two binomials that we're going to be multiplying out? Well, it looks like a difference of 2 squares, right? I have like a minus b times a plus b. Usually good things happen if you kind of multiply those things out or can factor those sorts of things. So I go ahead and multiplied that out. What do you see here? Yeah, I have a minus secant and a plus secant. Let's get rid of those bozos. So I can do that. Now what? Allison? You could change the secant squared to 1 over cosine squared, but is that making things simpler or maybe just a step sideways? I don't think I'd want to do that either. Maya? Yeah, so if I look at this, when I see a squared trig function, plus 1 or minus 1, first thing that's going to go through my head is to look at my Pythagorean identities. And I notice this one has a 1 and a secant squared in it. Although they're not together, I could subtract 1 from both sides. And then there is exactly what I need, right? So I think the best course of action here would be to replace that secant 1 with tangent squared. So we've done a little bit better here as we got rid of the addition and subtraction, so that's good, right? Getting simpler. We're down to just like division. Can we do any better than this? We can. I wouldn't do that. I would use another identity here. So there's lots of options for tangent squared. The option that I would be looking for is one that involves another sign. Because I have that sign squared in the denominator. If this is going to get better, something's going to have to cancel out with that sign squared, right? Look at the quotient identities. I see that tangent is sine over cosine. So I know that tangent squared can be sine squared over cosine squared. And here I'm going to just now divide my fractions. So to divide fractions, we multiply by the reciprocal. Everybody's okay there? And what good thing happens when I multiply by that reciprocal? Juliana? Sure. So we got rid of that sine squared floating around down there. That's good. Can we make this not a fraction? Yeah, so I noticed that 1 over cosine is the same thing as secant. So 1 over cosine squared is just secant squared. And that's as good as I can do because now I'm down to a single trig function. Everybody okay with that idea? Just worth pointing out, is the way that we've done these here in class the only way that you could get to this same answer? Definitely not. There are lots of possible routes. Some of them could be a little bit more circuitous, like you're taking the scenic route to get there. But it doesn't make it wrong. If you do things that are correct and you end up with the correct answer, Even if you take 15 steps to do something I did in 3, I would not give you a deduction for that. But it's usually in our best interest to look for the quickest way to do things, right? A good mathematician is a lazy mathematician. So let's do this one. We have cosine over 1 minus sine over cosine. What do you want to do first here? Okay. You could. Is that simplifying this at all, though? So 1 minus sine squared is cosine squared. 1 minus sine is nothing, unfortunately. So Ben, you are correct. You could do that, but I still have 2 terms. I still don't have any way to combine those 2 terms after I do that. So I'm not sure that's the best route, although it's not wrong to do that. I just don't know that it's gotten us any closer to a simplified answer. I would do an algebra thing first. Right now I have 2 terms, right? Those 2 terms are a fraction. If I want to turn them into 1 term, I would need to make a common denominator so I could subtract those 2 fractions together. That's what I would do first. What would the common denominator be in this situation? Exactly. 1 minus sine x times cosine x. So this first fraction, I'm going to multiply the top and bottom by cosine x. And the second fraction by 1 minus sine x. And I'm intentionally not distributing the second part of my numerator there. I'll explain why in just 1 second. It's not that I'm not going to do that. It is what I'm going to do next. I want to make sure that I point out a place that we can make a little mistake here. So when I distribute out this second part of my numerator, I have to make sure I'm taking the negative sign with me. I would say that, I don't know, half or so of students would make the mistake of writing minus sine squared because they didn't distribute the negative with. And notice that I am not distributing out the denominator. I'm doing that intentionally. Remember last year when we added and subtracted rational expressions? We never multiplied out the denominator because if we were going to simplify later, we'd want the denominator factored form anyways, which is what we have here. Now, because we're involving trig functions, there may be situations where multiplying it out, something nice happens. But I'm not doing that right away. That would be a final step. I want it to check for any reducing before I start thinking about multiplying anything out. So I'm always going to leave that denominator in a factored form until I can see that there's no reducing left to do. Then I would consider multiplying things out, not before that. All right. Let's look at this. Do you guys see anything nice here? Angela. Yeah, we have a sine squared plus cosine squared staring at us right there. Now it's a little bit hidden because they're not right next to each other, but shoot, that doesn't matter. They're both positive, so I do have sine squared plus cosine squared. So I can say that's 1. Now what do you see? We can reduce, right? Good. So we're left with just 1 over cosine, which is secant. Can we do any better than that? No way, Jose. That's a single trig term. That's as good as we can do. Okay, what if we wanted to do sine x times cosecant of negative x? Is there any algebra thing to do here right away? No, you should have 2 trig functions multiplied together. The best we can hope for is that somehow these things are going to kind of cancel out a little bit and leave us with a single trig function. What would you want to do first here? Allison? So we don't have cosecant, we have cosecant of negative x. So I could write that as 1 over sine of negative x. That's okay to do. But I would do something before I did that. I do want to do that, though. I will do that, but I would do something first. What was that? Yeah, so I can use my odd-even identity to rewrite that as negative cosecant of x. And then, as Allison suggested, we can rewrite cosecant as 1 over sine x. And whoa! Look what's going to happen. Can we do any better than that? Heck no. You got a 1 or a negative 1 out of there? You can get a constant. That's like golden right there. All right. What do you guys want to do first on this one? Yeah, right? Let's get rid of that. And that is one of our cofunction identities. That can just turn into a sine y. What now? Okay, so James says let's add cotangent and tangent. To do that, though, I'm going to have to rewrite them using the quotient identities. Because right now, cotangent, cotangent, they're not like terms. I can't add them together. However, I know that cotangent is equal to cosine over sine. And tangent is equal to sine over cosine. And there, we can add these 2 fractions together by making a common denominator. What would the common denominator there be? Sine times cosine. So the first fraction, we will multiply by cosine over cosine. And the second fraction by sine over sine. Giving me this. What do we notice that can happen there? So two things can happen, right? That is a Pythagorean identity. That's just one. Also, what else can happen here? I can do that. Everybody okay with that idea? So what am I left with is 1 over cosine y, which is secant. Now notice that all of these have kind of turned into secants. Is that always going to happen? No, that was just like a happy little accident. Right? All these examples have basically reduced down into secant. All right. For section 5.1, obviously we have the exam or the test tomorrow, so you don't worry about the homework for tomorrow. The next time we meet, though, you guys should have 1 through 14. Is that Thursday then, I think, is the next time we meet? After the exam? I think so. It's on the calendar. I'm sure I have it right there. I try very hard to make sure the due dates are right on the calendar. I'm pretty good about that.